So today's topic is energy conservation for greenhouse, or maybe the more not modern term would be energy efficiency, since the word conservation kind of has gotten a negative tone, meaning you have to sacrifice, and that's not the case these days. This group of seminars was made possible by a grant from SARE. It's a regional grant for the North Central region to put on this group of energy webinars, because that was noted that educators wanted more information on this topic. So the first thing we're going to do is just kind of look at the energy use in greenhouses. Energy is usually about the third highest cost for a greenhouse, about 15%. It's creeped up in recent years because of increases in energy costs and price pressures from the retail side, which has kind of shrunk margins for greenhouse growers. You know, about the third highest cost, 70–80% of that is for space heating. So a large percentage for space heating. About 10 to 15% is for electricity. Now, as you go south and we have more ventilation needs, those things flip. But here in the upper Midwest, that's about the way the breakout. Now, as we look at the greenhouse or growing conditions or growing chambers, we've always got this balance between making sure the plants will grow and the economics of it. So, for instance, we need light transmission for plant growth, but we also want to reduce our energy costs. Well, we can grow them in a warehouse and use artificial light, or we can put on maybe double pane or triple pane glazing, where we reduce the light level. So we have to take, and that slows down plant growth and actually can extend the heating season. So we have to weigh those things. We've got environmental conditions in the greenhouse we got to control, like humidity, which may increase energy use because we have to ventilate the moist air or dehumidify it somehow. Structure costs can be effective. We use glass. It's very heavy. And operating costs can be affected on our choice of how we construct that greenhouse. For the principles of heating, we're going to kind of hit all these today. But just I thought I'd little principles here. Conduction heat loss is the heat conducted or transferred through a material. I usually go by U value for a greenhouse, but you may be more familiar with an R value, which is used in the construction industry. Well, basically, the U value, not a very good U, equals 1 over R. So the R value is the inverse or the reciprocal of the U value. So I like to use U value because, being an engineer, it's BTUs on top, so that's my energy units. The other next thing is convection heat loss, which is heat exchange from moving fluid. So we do get this in a greenhouse. We get the air moving within the greenhouse. We get air, hot air rises. It rises up to the glazing. The hot air is cooled from heat transfer through the glazing materials, and then the cool air drops down. So that happens within a greenhouse. We have radiation heat. That can both be from the sun and from, if you warm an object and the object is warmer than the air around you, it will radiate heat out. So once at night, for instance, when the temperature is dropping, we can get radiation off the plants and soil and dirt and structure within the greenhouse. The next would be infiltration heat loss, which is basically exchange of air between the interior and exterior of the greenhouse through small leaks or holes in the shell. So if we've got warm air leaking out, we've got cold air replacing it, we have to heat that up to maintain our set point temperature. All these conditions work for all different sizes of greenhouses. But one of the big things we'll find as we get to smaller greenhouses, is that we have more surface area per covered area. So my first little thing here is to show you about what I call structural efficiency and just the advantage of a gutter-connected greenhouse versus standalone from a heat loss standpoint. And the main thing is we have lower heat loss because we have less surface area. We can get better space utilization. The heat loss area per floor area is about 1.5 ratio. So we have 1.5 area of covered area versus 1 unit of growing area or floor. With a standalone greenhouse, we have the advantage of isolated growing conditions. So we can have different heating or different climates within those greenhouses versus if we have one big greenhouse. We can heat them as we fill them. With a gutter connected, you'd have to have some drop-down walls if you want to isolate it or have, not heat the whole thing completely. It's easier to do natural ventilation with a standalone greenhouse, but we have a higher heat loss area per floor area. So then that's based on a 3,000 square foot greenhouse, which is, I think, 30 by 100, which is kind of roughly a typical commercial size. So the question here I pose is what shape has the lowest heat loss area per floor area? Because if we can get to that shape, we're going to maximize or minimize our heat loss and maximize our growing area. Well, if we look at shapes, a sphere or a semi-sphere has the lowest. Well, that's not real practical for building a greenhouse. The more practical would be a square. So if we can get it toward a square, that's going to help minimize our heat loss area per growing area. So just to put this in some dollars and cents, I'm going to use greenhouses with glazing. It's double poly IR, which we'll talk about later. About a half-acre greenhouse. I got some black fabric on the floor, which we found anecdotally absorbs some more heat. We've got power vent heaters, which have a seasonal efficiency of 78%. And we're looking at Farm A has 8 individual greenhouses versus Farm B has gutter-connected greenhouses, otherwise all things being the same. And we see from this example, we got quite a 2,400 gallons of this is LP gas or propane, about an 18% savings. Now, one of the things you see here is, because I got to select what size this is approximately a square. So I try to maximize or minimize my heat loss area in this example. Now, if you're starting out, the gutter connector or the standalone greenhouses are fairly inexpensive. The thing I like to suggest is instead of doing a standalone greenhouse, put up a small gutter connected, maybe a 2-bay, shorter gutter connected, because you can add bays on, you can add length on as you grow. And then you get the advantages of a little less heat loss area in the future. Maybe not to start with, but in the future you will. Orientation of greenhouses. This is important to maximize our sunlight. So if we have a standalone greenhouse or a single span, we want to maximize the sun. We want the orientation to be east-west. For gutter connected or multiple bays, we want it north-south, and that's mainly because the gutters will pose a shadow, and in the fall of the year or during the early spring months, that shadow from that gutter will stay in one spot, and you'll get less growing in that area because you don't get the sunlight. So that's the main reason. We look at glazing materials from a heat loss standpoint. I classify them in two classes. One is a single pane, and I've got single pane glass listed here, but single pane versus a double wall material. I've kind of gone on the both ends of this. A single pane glass is kind of the king as far as light transmission, but it is the highest heat loss, which can be an issue, versus double poly, which has the highest or lowest heat loss of the bunch. It's low cost, but it has lower light transmission compared to a single glazing. Now, the glass is king, and a lot of growers swear by it. It does require a higher structure cost because of the weight of the glass, and it's very long life unless you have problems with hail. So those are some of the advantages of that. Now, if we look at a comparison of a whole bunch of different materials, so I've got glass here, I got acrylic, which actually is a really good replacement for glass. I got polycarbonate, fiberglass, which isn't used very little on commercial greenhouses. You might find it a little bit on some hobby greenhouses, and polyethylene films. One thing you'll notice is on heat loss, which is this column here, conduction heat loss, almost all the single materials are the same heat loss, 1.1 to 1.2. All the double wall materials are about 0.5 to 0.7. So they all kind of follow in the same range. So we really don't care what material it is. We only care if it's double or a single layer. Now, as you get a bigger air gap, and you see I've got a range here on this polycarbonate, as you get a bigger air gap, you'll get some additional savings in energy from a conduction standpoint. The other thing you'll see here is light transmission, which is the first column. Your singles are all about 90%. Actually, this acrylic is one of the higher ones. So they're all about 90% roughly. Polyethylene is a little lower, but they're all about 90%. When you look at all the doubles, they're all about 80%, with the exception of this one's the one that stands out. Acrylic is excellent in that regard. So you see what I'm getting at. Life expectancy varies. Polyethylene films are the shortest. Glass and acrylic are the longest. This second column is IR, or infrared radiation. So this is the amount of radiation long-wave radiation that could leave the greenhouse or come into it in that regard. Almost all these materials are really good except for polyethylene films. Now, next thing we're going to talk about is an IR polyethylene films. These are inexpensive, but where this is, the IR is on a cold winter night when you got a clear sky. You get radiation. It's cold body syndrome, where you get radiation to the night sky. And if you're going to put polyethylene on, we want to use this double IR, especially in northern climates. The last column here is flammability. For growing conditions, we don't care about this as much, but for your insurance company, they do. Many of these are high. Acrylic actually does pass. The newer acrylics do meet fire code. So even though they're higher than some of these others, they do meet fire code, and thus is actually a pretty good material. So moving on, we're going to talk about how infrared pathways, where we look at the sun. We get the sun coming into the greenhouse. It warms surfaces and things in the greenhouse. They're going to re-radiate infrared radiation or long wave. Sun is short wave radiation. Some materials, like polycarbonate or glass, will reflect that radiation off and try to hold it in the greenhouse. When you get a plastic film, it tends to go through it. with the exception if we have condensation on the inside, then we'll get some reflection of that back into the greenhouse. So one way we can, I'm jumping ahead of myself. So, we get solar energy. It's absorbed by the plants and the sun and the soil. It can re-radiate through long-wave radiation. We heat those objects, and it can re-radiate. I already covered this. Glass and plastic are pretty good. Polyethylene's not so good. So what we can do is to buy films with this IR additive in it. They cost about $1.50 more per square foot. They save you 10 to 20% on a annual basis. So when we look at that in the northern climates, the payback is about 2 to 3 months or one heating season. Like on a 30 by 96 greenhouse, it's going to cost you about $40 more, so about $10 a year. So you more than make up that in energy savings. There's no loss of light transmission through that. It actually diffuses the light a little more, spreads it around. It's often combined with an anti-condensate, which is the AC. So each company makes one or two products that kind of fall in this range. So I've got some of those listed here for your reference. One thing to point out, the IR film should be, if we use a double layer, should be the inside layer. And the anti-condensate needs to be on the inside. So they only treat one side of the plastic sheet. It needs to be on the inside of the greenhouse. So that's important to point out. On the outside layer, we'd use a standard poly film. So we only need to buy one IR-rated film. One of the things we're concerned about with solar is that solar light equals a percentage increase in light equals growth. So that's pretty important. So we've already talked about the differences between them. Condensate can reduce light levels. So one of the things, if you've got a greenhouse that doesn't have anti-condensate film, or you made a mistake, you can buy the spray-on anti-condensate to put on. The other is in some areas, dust is an issue because of static. So they do make anti-dust additives as well for greenhouse films to try to keep those off. Let's see. The other issue on greenhouses we run into is they're taking warm air out of the greenhouse to inflate on a double poly greenhouse. Let me get a little drink here. And what can happen is we've got warm, moist air we're blowing into this, in between these layers. It hits the cold outside layer, and we get condensation, and it'll puddle right down in here. And sometimes, in some cases, it will get lots of water sitting in there. That happens for two reasons. One is it probably means we have a leak in our cover, and we're getting lots of air movement in there, as well as pulling warm, moist air in. So one way to do it is if we pull outside air, like this, outside air is going to be normally drier, and use that to inflate the layers. We tend to have less condensation in between. Now we may have some more on the inside, but there again, if we have lots of condensation on the inside, it probably means that we've got a leak in between those layers, and we need to look at how they're attached and sealed, and if we've got a hole someplace. The other thing we can do is use jumpers, particularly if you've got a standalone greenhouse. Sometimes you've got the material coming up over the peak of the roof. Sometimes they get pinched and you don't get very good inflation on one side. That can help alleviate that problem. Air exchanges, infiltration rates, we're concerned about that because we have to reheat air. We'd like to have low infiltration rates because that's heat that is escaping. So this is typically kind of busy work or housekeeping type stuff. Louvers, doors, holes, laps in glazing, all can, where the vent goes out for the heater, those are all potential places where you get infiltration leaks. Glass is typically higher because it's more joints, especially as it ages, so we don't get as good a seal. Double poly is the lowest typically because it has the fewest joints. You got one piece covering the whole roof section. So these are some kind of rough guidelines of what the air exchanges per hour may be. We've actually gone out and measured some greenhouses, and they fell right in these ranges. So these are some pretty good numbers. So you can see here, new glass or glass in good condition versus old, we can have a significant increase in infiltration. The other thing that can affect infiltration is wind. 15-mile-an-hour wind can double our heat loss. If we put a windbreak in, whether it's trees or some kind of wall, they can reduce that by 10 to 15%. That's a long-term solution to reducing energy usage. It can also help with snow accumulation and potential wind damage. So that's something we can do as a long-term solution on a greenhouse. So infiltration leaks, we typically can save 3 to 10% in heating costs by fixing the leaks. So it's, checking roof and wall vents to make sure they're tight and have seals. Make sure the cover's tight. Glazing and lap joints on glass are in good shape. Fix holes, weather strip around doors. And one of the reasons this picture is in here is these corrugated doors. These tend to be real leakers. You get leaks along the sides, and you get leaks along the top here. I would much rather see a standard overhead door in a greenhouse, but I know why they put these in. So if you had an overhead door, you'd get a shadow during the summer if you want to leave it open versus these. So one of the things you can do on these kinds of doors is put a plastic film over the outside so that you can seal that up during the wintertime, because that's going to be a large source of infiltration leaks. Door sills, especially we have dirt floors, because they'll get eroded away and you won't get a good seal around the door. I just talked about these roll-up doors. Ventilation louvers, make sure they close tight. We want to use a dry lubricant like graphite so they don't, if you get them clean and you lubricate them, you don't want to use like oil or grease because it'll just attract and make them not work faster. Cover up unneeded fans for the winter. Piece of plastic, a little foam. Plug gaps around foundations. I found this a lot in greenhouses. The ground settles, and then I have this leak under here, this hole under here, where these things will leak. And the other things, we have a glass greenhouse, and we don't have time or money to fix it. We can just put a piece of polyethylene over the glass, and that'll reduce the infiltration leaks in that greenhouse. Now, you're also going to reduce light level, so that's one of these balancing acts, which is going to cost more. Conduction heat loss through walls. There's no reason to have glazing down to the ground level if I'm growing on benches, so we can insulate the sidewalls. Now, this can be insulation like a foam board laid up against the sidewall. It needs to be sealed to the wall or it won't do any good. If it's just sitting up next to the wall, it's not going to provide any insulation value, but it has to be tight against the wall. North walls, any opaque surfaces could be insulated. There is kind of, some people will say that we get a fair amount of reflective sun off the north, so we shouldn't make all these should be translucent surfaces versus opaque, but that's for the grower to decide. And the other is insulating the perimeter, especially if I'm growing in the ground. Down to 24 inches below ground would be the minimum, 1 to 2 inches of foam. It's easy to do on new construction, a lot harder to do on existing construction, just because of the labor to put it in. Foam board is flammable, so we want to keep it away from stoves and stuff, and I'd recommend they have foil-backed foam board. I think Dow Chemical makes some, or Dow Corning. Very nice material, and actually they have some newer materials. I was just on a job site here a week ago. They were doing a cooler, and they have a board that's actually basically has fire retardant in it, so it is not very flammable. Thermal curtains, these can save us 30 to 50% on heating costs. We're going to talk about those on Thursday at great length, so I'm not going to talk about it too much here, except that these are the shades here, and these move back and forth to close the greenhouse. They are an excellent way to do it. I know some people have suggested we use triple pane materials on the roof surfaces, and I frown against that because you're going to lose light. I'd rather see you invest in a thermal curtain, which has multiple purposes and can save much more energy than if we use triple pane material. Unit heaters, or heaters in general. Unit heaters are used in lots of greenhouses, especially smaller ones, even some bigger ones. They have the advantage of lower cost, ease of installation. Low installation cost, too, goes along with it. They can be easily staged and are very reliable. They've been around for a number of years. There's 4 different types. I want to go through the types so we can understand what we're looking at, because you can just look at them and be able to tell once you know what you're looking for. The first in the upper right-hand corner is a gravity vent heater, and the big thing you can see is you've got a pipe going out of this, a large diameter pipe going straight out of the back of the heater and venting outside. What's different between that and the power vent heater, which is right below it, is the power vent has a little fan on it, and the fan meters the air out. Otherwise, it's the same heater. It just has this little vent kit on it to push the air out. Well, the advantage of that is when the heater is not running, that fan basically blocks the air from leaving the heater, so that we don't get air going out of the greenhouse. And we're going to talk about that in a minute as to why we always want to use a power vent and never use a gravity vent. The next step up on that is called separated combustion. This is a power vent here. Here's the fan up here in the top, but we have an air intake that's separated from the inside of the greenhouse. These are advantageous, especially where we have where we're using lots of fogging and spraying inside the greenhouse, because some of those chemicals are detrimental to these heaters and chew them up real quick. So that would be the difference. The next step has actually only been out there's a company that's been out for quite a few years, but Modine just joined them. This is their heater. It's a high efficiency condensing type unit. So these are 93% efficient, versus the others have a thermal efficiency of 80%. So quite a jump in energy efficiency. And you can tell these, one, you have PVC tubing going in and out usually because you have low exit temperatures, and you'll have a condensate drain, which is down on the bottom. So you have to have a place to drain that. It's very acidic water coming out of there, so we need to drain that off. So what's different on these heaters than the others, they have an extra heat exchanger to condense some of the moisture in the flue stream to get a little more heat out of that. So when we look at these heaters, I already said the first 3 were 80% thermal efficiency. The next one, the condensing unit heater is 93%, and they all have varying costs. Now, this first one, the gravity vent, there are lots of them installed, but they are not sold anymore. As of 2 years ago, they're basically off the market, or maybe it was a year ago. You can still find a few companies still trying to get rid of them, but they don't meet the new energy code, which requires a damper in the system when the unit isn't running, and you can't have open pilot lights anymore. It needs to be an electronic ignition. So when you put those two things in, the cost difference between these was about $80 to $100. So it wasn't worth keeping a gravity vent heater, because once you put the separate damper and different pilot light in, you've got the same cost as a power vent heater. So you can see various costs here. So let's investigate this a little more. These are the costs are manufacturer's list price. In many cases, you can buy them much cheaper than that. Thermal efficiency is basically the instantaneous thermal efficiency. So that's the heat out that I get out of the heater versus the heat that in the fuel that I use to run the heater. The other thing that is not talked very much is called seasonal efficiency, and this accounts for the air that I'm combusting that's already been warmed in the greenhouse or leakage, and this is where the gravity vent heater falls down, because when it's not running, I have lots of heat going out of the greenhouse through that big pipe. Whereas the power vent heater, that has that fan in to reduce that amount of air leaving. So it's got 78% thermal efficiency. It does use air from inside the greenhouse, which is basically 2% of the heating. Separated combustion uses all the air from outside the greenhouse. A condensing unit heater, that uses air from outside the greenhouse, but it is highly efficient. So you can see the difference between these. So, in some cases, we can take this gravity vent heater and replace it with a power vent and get a nice energy savings. Although I'm going to show you in a minute how we can justify the higher cost of a condensing heater. So here we're going to do a little case study here. We're going to look at a 30 by 96 greenhouse. I picked Madison just because that's where I'm from. And we're going to use 2 LP gas heaters on this. One of the heaters can provide heat 90% of the time, so it's just 10% of those really cold nights where it can't keep up. We're going to use daytime temperature of 68, nighttime of 60. LP cost is $1.50. That's a moving target, but that's what I'm using for this example. And February to June heated growing season, so just a spring bedding crop. So I've got 2 charts here. The first one uses a gravity vent as my base. And I've got the incremental cost in this first row of that heater versus the gravity vent based on the historic cost of that. The estimated fuel use using a mathematical model, heat loss model. The fuel savings in both percentage and dollars, and the simple payback. So this is the energy savings versus my incremental cost of buying the heater. So that would be 180 for this first one divided by the 624. So on this power vent versus a gravity vent, my savings looking at incremental cost is 39 days. So that's a no-brainer. You want to do that anyway. Separated combustion, that's my power vent with separate air intake. That's quite a bit more expensive and a 4.6-year payback. Still not too bad. The next one is my high efficiency condensing heater. It's basically separated combustion type, and that's 3.5 years. So it's actually a better deal than buying the separated combustion because the cost difference wasn't that great, but I get another 11% in energy savings. So that's a pretty good deal. Now the last one here I put in, since remember I said that one heater can heat the greenhouse about 90% of the time, and it's just those few cold nights. So this last one, I teamed a high-efficiency condensing heater with a power vent heater. So the condensing unit would be the primary heater, the power vent would be the secondary heater, so if the first one can't keep up, the second one would kick in and provide the additional heat. When we do that, yeah, we lose about 3% in energy savings, but we bring the simple payback down to 2 years. So that's actually the best combination of it. Now, reason we recommend that versus 2 heaters versus going to 1 big heater is basically for backup. If one should fail, we don't want to lose that crop. That's our bread and butter. The next graph here I did the same thing, but I used the power vent heater as the baseline because you can't buy the gravity vent anymore. So this, it's very similar. The separated combustion is a huge, as far as simple payback, you'd never do that. The high efficiency condensing unit, 2 of those was what we need, so that's a 7.5-year payback. That's a little long. But if we do the combination of condensing unit and power vent heater, then we get it down to about 5 years, which most people, that's not too bad. That's a 20% return on investment. So that would that's in the realm of what most people can do. And if you're using natural gas, you might be able to get an efficiency grant to help with that. Now, if you've got a gravity vent heater, all is not lost. There are companies, some of the companies make power vent heaters or power vent kits that can be put it on a gravity vent heater, convert it to a power vent, pay for itself in a season or 2. So that's a good deal. Now, there are non-vented unit heaters out there that people claim that are as good as, or you'll get more energy savings. Well, if we look at the thermal efficiency alone, that's true. But if we look at the seasonal efficiency, that's not true. These heaters put all the products of combustion into the greenhouse, including the moisture, which a vented heater doesn't. And you lose about 8% just turning the moisture into vapor. The water that happens as a product of the combustion process. And then you've got to bring some air intake because you've got to replace that oxygen that this heater is using from within the greenhouse. So you end up losing, another 10% roughly, and it depends on how cold the air is coming in. You lose some more. So they're about 80%. So these are really no better than a power vent heater. Now, they are good for plants in daytime because they increase CO2 levels, but 80% of our heating happens at night when these would be running, so they're not very good in that regard. So my suggestion, if you're interested in one of these, use one of these instead of a power vent heater. Use a high-efficiency unit heater, and one of these is a backup. So it's going to run a little bit on those cold nights, but then you set it so the power vent runs at night if it needs heating, or the high-efficiency condensing runs at night if it needs heat, and the power vent, this non-vented heater would run during the day to provide CO2 increases so the plant can use that. One of the things with increases in humidity levels can be plant diseases can be an issue. If we get condensation on the glazing, then we have lower light levels. So those are some issues. these heaters must have fresh air intakes. So they're either connected to the heater or they have to be intertied with a vent. That's manufacturer recommendation for these, is that they have a certain vent size and the vent has to be open when the heater is operating to keep from starving them from oxygen. Just a little quickie is, we sometimes have people that have greenhouses where we don't have electricity. It could be a hobby greenhouse or Amish, for instance, that don't use electricity. These little non-electric heaters can work fine. These are actually, some of them are vented, some of them are not vented. But they put the air in the greenhouse by convection, so we're not necessarily going to have very good distribution, where the other ones have fans on them to move the air around. They tend to be low BTU per hour capacity, so I'm probably going to have multiple ones in a greenhouse. So that's not bad because I can stagger them through the greenhouse to get some more even distribution. They do have different types of thermostats. I'd recommend the setback, so you can have a day-night setting, and that the thermostat should be set away from the heater. And these are usually battery operated. What we don't recommend is to use these portable heaters. And the reason for that is ethylene gases and sulfur dioxide and carbon monoxide. Ethylene gas is detrimental to many plants, and unfortunately you won't see the effect for a couple of weeks. But they can cause all kinds of troubles, and kerosene and oil are the worst. You can have some of the same symptoms with natural gas or LP gas, but a lot less. So tomatoes are particularly susceptible, but there's other plants as well. So don't use these. If you're forced to use them, you need to crack a door open so you get plenty of ventilation. Heat distribution, location, in-floor heating, if I'm growing on the floor. What we're trying to do with this stuff is create a microclimate. We can do under bench or benchtop heating. This is an example of a benchtop heating. These are little capillary type tubes on the bench that I put my plants on. These can reduce heating costs by 20-25%. They can be hydronic or forced air. I'm going to show you a picture of forced air in a minute. We can get increased plant growth and yield. A study out of Louisiana showed 7% increase in yields for tomato plants. I'm going to show you a forced air. You can use a poly tube on the end of a blower to do it under bench. It's approximately equal to turning the thermostat down 5 to 10 degrees. I really don't care what the temperature is at 6 feet. What I care about is what the temperature is right here at the plant environment, because that's the only thing the plant cares about. So here's an example of a unit heater. This has a blower on it versus a propeller fan. It's forcing the air down through a tube, and then this comes and has a 90 with a poly tube on it underneath the bench to distribute the air down the bench. Another way to do it is with fin tubes. On the left here, or on the right, we've got some homemade jobs where we've got a feeder pipe and then pipes going underneath the bench. Here's somebody that's used a residential fin tube and just bare pipe underneath the bench to raise it up. And what you can do in some of these to try to keep the heat underneath the bench, you can put like a fabric cover around the skirt, around the edge of the bench to help retain that heat and make sure it comes up between the plants. On the left here is a commercial product. This is a fin tube. There's a couple of companies that make that kind of tubing. It's a low capacity tube to put the heat underneath the bench. So that's an example. Here's an example of Amish doing the same thing. He had a boiler sitting over here in the wall, and the heat come up across. There's no pumps in the system. Come down. Here's a distributor across the back here, and then here's my pipes that come down underneath the bench. This was just made out of irrigation tube that came down underneath the bench. So a very ingenious way. And then this this tube returned to the boiler across the floor. So pretty ingenious way to do it. Heating maintenance can save us some money. One is insulation of pipes and head houses and ducts. Make sure we have air exchangers are clean. Lubricate motors and fans as required by the manufacturer. If we've got a boiler, like a fire tube boiler, we need to remove the soot. That can reduce fuel consumption by 10%. Steam trap maintenance, if you're using steam, is really important because that can be lost if they're not working correctly. Especially with oil burners, we need to change the filter and check the nozzle. They get plugged real easy and don't atomize the fuel very well. Thermostats. If the thermostats are not working properly, you're not going to get the right temperature, and it may make things work more. So you could get up to about a 20% savings if you had a system that's in really poor condition. The other thing is to make sure you provide intakes for boilers and unit heaters. If you walk into the greenhouse on a very cold night when everything's running and you smell products in combustion, that means you don't have enough air intakes. So you probably need to put an air intake, try to bring it in right to the heater if it's not a sealed heater. You can bring that right into the heater to provide the air right at the heater. And that could be have a damper on it so it opens when the heater starts running. High efficiency boilers. If we're going to use a hydronic system, they make these little modular boilers that are 90% plus efficient. They're hot water. They're modulating up to 98% efficient, some of them. So one of the things we can do is if I have an existing boiler system and it's really old and dilapidated, what I can do is I can put these boilers in and make them the primary, use the existing boiler as a reservoir, and so when it calls for heat, these little modular boilers kick in to provide the heat. If they can't keep up, then the old boiler will come in as a secondary heater to provide the heat. So that's another way to do it. If I'm doing a hydronic system, then I'm going to use some water to air exchangers. So these are some pictures of a couple. So these can be set, this one can be set on the floor underneath the bench if we needed to, versus overhead. So that's another way to use those boilers and distribute the heat. So I can combine a under bench heating or in-floor heating with some air heating as needed. Because on a very cold night, if I have in-floor heating, I'm still going to need some overhead air heating because a floor heat system can't release the heat fast enough to keep the plants warm. Another type of heating system is called a radiant or infrared heating system. These are used lots in warehouses and stuff. There are companies that make them for plants. I'm not a real fan of them, but there are people that use them and use them successfully. What these do is they heat the objects and not the air. So what the disadvantage is they can burn the plant leaves. So that's kind of what you have to watch for if there's a problem. Some of these systems don't distribute the heat very well down the length, so you get a hot spot at one end versus the other. At least that's my personal experience with some of these systems. So that can be an issue. I think the best place is loading docks and work areas, so from a transplant area, a warehouse. Those are some of the places I think are best, but here I've referenced a publication from one of the companies that sells the product for that use if you want to investigate that more. Environmental controls. One of the things that we're concerned about if we have all individual controls is the controls fighting each other. So if I have heaters and fans on different controls, the heater comes on, heats it up. If I don't have my set point for my fan set high enough, all of a sudden my fan kicks in, takes the heat out of the greenhouse, cools it off. So I've got this oscillating of heater versus fan versus heater versus fan, etc. The other things we want to make sure these vents are open before the fans comes on. We might be doing lighting, so we might be using a daylight integral controller. We want to make sure the lighting. But the other thing is, when I'm doing CO2, I don't want the fans on if I'm putting CO2 in the greenhouse, because then I'm just taking out what I'm trying to put in. So trying to make these things work together and use the same sensor point is the other thing. The other thing, some of the newer controllers actually tie the environmental controller to a weather data site, either at the greenhouse site or far, and that way we can anticipate. So if you see the wind come up, you might want to close the roof vents, or if the sun goes under, we might want to close the roof vents, because we know that it may cool off, especially on a cooler day. The other advantage, if we've got a controller, especially a day-night thing, is we can take advantage of something called DIF, day-night differential. Plants see the average daily temperature. So if it's 75 during the day and 65 at night, the average is 70. Well, that's the same as if I had the temperature set at 70 the whole time. The plant sees that as the same. So I can save about 5% in fuel costs by doing that, because if I can lower my temperature at night, that's when my most heating occurs. So that can be a savings if I have a lower temperature differential between the inside and outside of the greenhouse. Next thing is space utilization of greenhouses. If I can pack more into that greenhouse, then I get more product per unit of energy put in. So if I look at a traditional bench system, I got 59% growing area versus 69 for a peninsula type system versus 81 for a movable type bench. So these movable benches, they're in here, and you can just move this bench over, and then that open up a gap here, so you can work on these two sides of the bench. The movable bench isn't very good for retail space. The peninsula, depending on the width of these aisles, may or may not be. But one of the things we consider, if we have these movable benches on wheels, we might be able to take a few of these out of the greenhouse and spread these out and make them into a peninsula type system. So during the cold of the greenhouse season, I can pack them in there. But once it starts warming up and my retail season starts, I can take a few benches out and spread these out and get the advantages of both. Here's an example of a movable bench system. Here's my heating tubes here. We've got irrigation on top, and these roll-on pipes. Here's a pipe here. This rolls so this bench can roll over here and open up an aisle on the other side. So just an example of a system. The other thing I can do is racking. I can put plants that don't need so much light on the bottom versus plants that need lots of light on the top. So I can use this kind of system to get more in per square foot. I can also use hanging baskets, which I'm sure many people use. The disadvantage you have here is I'm blocking light, because if I have plants here and I have plants down here in the bottom, I'm going to be having some shading, so I'm blocking light. So you have to make sure of how you're putting the system. Now, there's a couple different types of systems. This one's on a pipe system that actually moves this from end to end of the greenhouse, so exposes the floor of the greenhouse from time to time. Over here, this is a cable system, and actually got a water. Right in the middle here is a water to get rid of one of those chores of trying to water the plants, which is a labor-intensive process. Circulating fans. We talked earlier about convection heat loss. Hot air rises, so if I'm heating the greenhouse, I have to heat the whole greenhouse volume to get down where the plants are growing to the desired temperature. Well, if I can use some kind of fan to stir that air up, then I can reduce my heating to some extent, because I don't get the heat up here on the roof. So you can use a paddle fan. Here's a newer type fan that's come out on the market, little Venturi type fan. or the traditional one is a basket fan. These two are going to provide a air pattern that's going to be down and out. The basket fan is basically going to provide a rotating around the greenhouse and is the preferred one thing. The other thing fans do is they help drive leaves faster to try to prevent disease, especially after watering. When I look at ventilation fans or exhaust fans, there are great differences in the efficiency. Efficiency of fans is rated as CFMs per watt, so air moved or cubic feet of air moved per watt or unit of energy. So if I look at a 48-inch fan, if I look up on the test data, it can go from 12 to 27 CFMs per watt. So it's quite a big volume. Best Lab, which is part of the University of Illinois, actually does these ratings, and you can buy it in a hardcover or you can get online and get these ratings for free. What our general recommendation is for a 36 to 48-inch fan should be 20 CFMs per watt at a 5/100ths of an inch of water pressure difference between the inside and outside of the greenhouse. Larger fans are more efficient than smaller fans. Excuse me. And the other thing to look at is if you have to replace a motor on a fan. Many of these fans are more efficient because they have a more efficient motor. That's a big component of the efficiency. So going back to the manufacturer can be an advantage. So if I have a 1 horsepower fan, which would be a common size, 67% efficient for a standard motor versus 82.5 for a high efficiency motor. So yes, you're going to pay more for that motor, but it's going to save you energy in the long term because it's more efficient. Fan maintenance, this can be shutters. If the shutters don't open freely, they can reduce airflow. So you want to clean them and lubricate them with a dry lubricant. Belt tension is a big one. Loose belts can reduce airflow by 30%. I recommend automatic tighteners if you're going to buy a new fan or retrofitting them. Weeds and brush outside can impede the air movement. And we should be using totally enclosed motors in all cases. The other thing is the guards, to make sure the guards are clean on the outside. So a lot of maintenance type things. Ventilation in general, we can use shade curtains, which we're going to talk more on Thursday. They can reduce the air temperature underneath that curtain. We can use they can be external or internal. We can use evaporative cooling systems to reduce air temperature. We can use misting, roll-up sidewalls, open roof designs. That's what this upper picture is showing. This is a roof that opens up and lets the air out. This happens to be a half-acre greenhouse with no fans. They open the doors and open the roof, and you get a nice breeze through it. And then variable speed fans can help. You can take a large fan and slow it down for the winter and speed it up for the winter or the summer to take advantage of the efficiency. This lower picture shows roof vent to the top, and then these are sidewall. This is a blow-up type one that inflates to raise it up and down. So here's a picture from that greenhouse on the inside, seeing the open roof area. So you get a very large vent area. That's one of the advantages. One of the things, we haven't measured it, but we're pretty sure that we get increased infiltration loss too. So there again, it's a give and take as to what we get. For naturally ventilated greenhouses, we have an air inlet on the bottom and one on the top typically, or you have one side to side so the air blows through. That's the other way you do it. But you get thermal buoyancy, and you also, in more cases, you get the wind coming across that acts like a venturi to pull the air out of the greenhouse to get air movement. Pneumatic, if you don't have electricity, we can use pneumatic vents to open a greenhouse. So for a hobby greenhouse or somebody that doesn't want to use electricity. Some of these are adjustable over a range. They gradually open over, say, 20-degree temperature range. The weight of the door you're trying to open, some of them can't open very much weight, so sometimes you have to counterweight them or come up with some ways to do that. But that's just another way to vent a greenhouse. Here's a picture of roll-up sidewalls. These are great for summer ventilation, not so great in the wintertime. Because one of the issues is many of these are single-layer materials, and they have high infiltration rates because typically they don't seal them at the bottom and they don't seal them on the ends, so down here in the ends. I recommend you take a piece of film and put over the inside in the wintertime or the outside. You can either take this material and put a wiggle wire across the bottom to hold it down and one up the side. For the wintertime, you take it out in the summer so it can be used. If it's a double material, then you can inflate it. If it's a single material, do the same, but then actually put a piece of film on the inside as well to reduce that infiltration rate. It can be a substantial difference in the amount of air going through that. Supplemental lighting. We actually have another presentation we don't have in this series, but we did last spring on how lighting can help. And what you do is you use supplemental lighting. You measure the daylight integral, so the amount of light that the sun provides, and then you make it up with artificial light. And what this does, it makes it so you can predict time to market, which if you're doing something like lettuce or herbs or something like that, you can make sure you get them to market. The other thing you can do is you can plant later, so then you have less heating. And if you have enough light, you get better flowering, which if you're doing the retail floriculture, plants sell better when they have a few flowers opening on them at the time of sale. One of the things you need to know is that plants, there's a lot of difference between plants of how they use light, so you need to look at that. Plugs and liners can benefit by more root development with light, so that's another advantage. Types of lights that we'd used, a fluorescent light for growing chambers and high-intensity discharge lights for greenhouses. And typically, you're going to use a sodium light. They're the most efficient. They have on the red side of the spectrum, so they can provide some elongation that may not be desirable. The other thing you can do is mix them with metal haloids, which are not quite as efficient, but they provide more of a lighter, white or blue type light. And you might want to look at your electric utility. They may be able to offer you off-peak electric rates for those lights to reduce the cost of that lighting. So that could be an advantage. I'm going to kind of wrap this up here. Next few slides are on solar greenhouses. I get questions once in a while. I want to build a solar greenhouse. And I kind of respond, well, all greenhouses are solar. What do you really want? And basically what they're after is a greenhouse they have to provide minimal amount of heating for. And this is usually done with a mass, rock, stone, brick, something to absorb heat during the day and then give it back off at night. So this would be in the walls and under the bench, foundation, etc., floor, to absorb as much heat as they can. Cornell did a study where they put rock under the benches and blew air through it. They found they could replace about 25% of the nighttime heating costs with that method. It was a small greenhouse, so that may have had some effect because it may have had higher heat loss. But generally you can do that. The big thing is you have to allow the temperature to vary more than you would possibly for a commercial greenhouse, because you've got to drop the temperature below the temperature of your thermal mass in order to get the heat out. You have to create a temperature differential. So depending on the crop, it may not be advantageous to do that. So you probably will need some supplemental heating, especially in northern climates, although I've run into people that do have greenhouses that they don't need any heat for. But if it gets cold, you're going to slow down plant growth. So that's just something to know. Here's a couple of references. Solvia, which is an older book, but that's what this picture is of a greenhouse. It was on, I can't remember where it is located now. It's off of one of the islands off of Massachusetts. And then there's Passive Solar Energy Handbook. A couple books, and there's some others. Some of them are out of print. You have to look in the secondhand market to find them. So here's an example of a typical passive solar greenhouse. You have a south-facing glazing. Typically the walls on the east, north, and the north roof are heavily insulated. You typically will have a night curtain to minimize heat loss and barrels or something to have thermal mass in the greenhouse. So the advantage of these is during the winter time, the sun will get to the back and heat up the whole greenhouse. During the summertime, the sun will miss some of those thermal mass. So try not to overheat the greenhouse. So that's some of the advantages to that. So here's some examples. Here's one in western Pennsylvania, heated by the sun and some firewood. One of the things I'm going to point out is you need a distance, a straight section here for snow if you're in a snowy climate, because otherwise the snow will pile up in the front there. So there's a picture of one. Here's one in Colorado, and you can see they've got snow piled up in the front here. So you've got to leave enough vertical area there. But it can be, you can grow permanent beds in the ground, or it depends on what you're growing in the greenhouse to provide things. And the thermal wall can be used for holding plants, especially heat-loving plants. Just an example of what it might look like. And in some cases, for instance, this one here, I think they actually have an extra deck up here where you can grow plants, and then you can have a utility area down in the back here. Is kind of how you can lay those out if you want to do a big one. If you've got a greenhouse, you want to try to predict energy from a greenhouse. This is a tool that we developed for USDA, and in here is a greenhouse tool. So if you go to this website, you can get on there and it'll ask you a bunch of questions about your greenhouse and then give you some advice on what you might be able to do. Here's a bunch of resources that you may find useful. This particular one, this is a little out of date, but this Energy Conservation for Commercial Greenhouses is a very good one. If you're interested in lighting, this Lighting Up for Profits by Paul Fisher and Eric Runkle is also an excellent publication. So with that ends the presentation for this morning. And I'm going to go to see what we have for questions. And if you want to ask it personally, you can unmute and talk to me as well. So Lori asks, on the high efficiency condensing, it appears to be better north. For further north, the high condensing unit heater may pay back faster just because we're using it more than south. So that's another thing you have to, if you're down Kansas, it may not pay to get that extra expense of that unit heater. Maybe a power vent heater would work well enough because of the less heating required per year. Mark asked about the slides. So anybody that came on late, if you go to the top toolbar where it says feedback and you go 2 icons over, has a group of pages. That's where the handouts are. If you have trouble downloading them there, you can give me an email and I will send them to you. So in there you have additional resources. You've got the slides from this morning and a narrative for the slides. Since this is supposed to be a professional development, we put those materials together so that you can take these slide sets and either use them in whole or part for your presentations. And if you want the actual PDF, you can email me and I can send it to you. They will eventually be posted on eXtension. We're working on trying to get a site put together to get them up on the eXtension site. It's probably going to be in mid-June before we get that done. Any other questions this morning? Okay. Again, JD, I don't know who you are. I don't have you on my list. I would like to send you a survey. That's the other thing. I'm going to send everybody out a post-evaluation survey. Hopefully, if some of you got to the pre-evaluation survey, it's part of our SAYER grant was to look at how well we're doing as far as providing knowledge to you to do these programs yourself. If do we have any other questions? Well, hearing none, if you do have some more questions, you can email me and I will try to answer them. Otherwise, I hope that everybody will be able to tune on Thursday and we'll talk about thermal curtains, which it won't be as long a lecture, but you're going to find that thermal curtains are a good way to reduce our energy use even more. With that, I'll say goodbye for today, and hopefully we'll have all you on Thursday. Thank you.